All right, so we're ready for another deep dive. And this time, it's a pretty fascinating one, I think. We're going to be talking about plutonium-238.
Sounds exciting.
Yeah, it is. So we've got a bunch of sources here, a couple of scientific journal articles, a report from NASA, and a few news articles from pretty reputable places. So we're going to kind of dig into all this and see what we can uncover.
Yeah, let's jump in.
Okay, so I guess the best place to start is with like a real-world example. Imagine NASA's Dragonfly mission, right? This is that helicopter drone that's going to head to Titan. That's Saturn's moon.
Right.
1.5 billion kilometers away. I mean, that's
Yeah.
mind-bogglingly far.
It is. It is. And a pretty harsh environment, too, right?
Oh, totally. Super cold, this icy, almost alien world. And you know what's making this whole crazy journey possible?
What's that?
Plutonium-238. That's the
Oh,
key.
wow. Okay, so right off the bat, we've got this kind of paradox, right? This material, plutonium.
Yeah.
We usually think of it in the context of, the Cold War and nuclear weapons and all that scary stuff.
Yeah.
Yeah.
But now we're talking about it being crucial for peaceful scientific exploration. It's kind of wild when you think about it. All those countries, the U.S., Russia, the U.K., France, China, Israel, all racing to build up their nuclear arsenals. And it was mainly plutonium-239 they were focused on, right?
Yeah.
That's the weapons-grade stuff.
Right, yeah. And during that whole process of refining that plutonium-239 to make those weapons, other types of plutonium, what they call isotopes, basically kind of emerge as byproducts,
Yeah.
just sort of like nuclear leftovers, or so they thought. But NASA, they were smart. They saw something different, something valuable in one of these leftovers, plutonium-238.
Yeah, they realized that even though it's still plutonium, it behaves really differently from the 239. That's actually the key difference here. Plutonium-239, it can sustain that chain reaction. That's what makes a nuclear bomb go boom. Plutonium-238, it can't do that.
So it's not going to blow up. No, not at all. What it does do, though, is decay radioactively, and it gives off this really consistent, reliable heat as it does that. And that's the magic, really. That heat is what we can convert into electricity.
Ah, okay, so it's not about explosions. It's about this steady heat output.
Yeah.
And that makes it perfect for, keeping a spacecraft running for years, maybe even decades out there in the deep dark. Safe and reliable, like you said.
Exactly, like a long-lasting battery, but one that runs on radioactive decay instead of chemicals.
Okay, so we've got this kind of miracle fuel source for space exploration. It's powering all sorts of missions, right? I mean, think about it. The Apollo missions way back when, the experiments they left on the moon, those were powered by plutonium-238.
Yeah, the Voyager probes, too, still sending back data from way out beyond the planets after, almost 50 years now? Incredible.
Crazy. And think about Cassini orbiting Saturn, sending back all those incredible images, and those rovers on Mars, Curiosity and Perseverance, all running on plutonium-238. So clearly this stuff lasts.
Yeah, it does. It has what they call a half-life of about 88 years. So basically every 88 years, the amount of heat it produces is cut in half.
So it's not like it just suddenly stops working after a set amount of time.
No, it's a gradual decline. And because the half-life is so long, it makes it really suitable for these missions that need power for decades.
Okay. So we've got this fantastic material. It's proven, it's reliable, it's powering some of our most amazing achievements in space. But here's where things get tricky. We don't actually have a lot of it, do we? And why is that?
Yeah, that's the catch. The United States, we actually stopped producing plutonium-238 back in 1988.
1988. Why do we do that?
Well, think about what was happening back then. The Cold War was winding down. We had this huge stockpile of nuclear weapons already. So it seemed like the need for plutonium-238 had kind of gone away. They shut down the main production facility, the K reactor at the Savannah River site, and that was basically it for U.S. production.
Who just shut it off?
Yeah.
Just like that.
Pretty much, yeah. And to make matters worse, we also stopped importing it from Russia in 2010.
So we stopped making it ourselves, and we stopped getting it from anyone else.
Yeah.
And surprise, surprise, now we're running low. I mean, that sounds like a really bad plan in hindsight.
It does, doesn't it? It's like having this amazing battery for your flashlight, but then you decide to stop making those batteries, and you also stop buying them from the store. Eventually, your flashlight's going to go dark.
Right, exactly.
Oh.
So what are we doing about it now? I know NASA and the Department of Energy are trying to make more, right?
They are, yeah. They restarted production, but it's a slow process. Right now, they're only making about 550 grams per year.
550 grams, that's like, what, barely more than a pound? I mean,
Yeah.
that doesn't sound like much considering how much power these missions need.
It's not, and that's why there's this huge competition for the plutonium-238 we do have. One of the articles we read mentioned that the Europa Clipper mission, that's the one that's going to Jupiter's moon Europa.
Right, to look for signs of life in that ocean under the ice.
Exactly. Well, that mission, it was originally supposed to use plutonium-238, but they ended up having to switch to solar panels instead. And that's because all the available plutonium was basically reserved for Dragonfly.
Wow. Okay, so they had to redesign a flagship mission to explore a potentially habitable world, all because we don't have enough of this material. I mean, that really shows how crucial this stuff is.
Yeah.
Have scientists looked at any other options? Like, are there other radioactive elements they could use instead of plutonium-238?
Oh, yeah, definitely. They've explored a bunch of alternatives over the years. Like one of the very first generators NASA tested, this was back in 1959, it used polonium-210.
Polonium-210, how'd that work out?
Well, it actually produces a lot of power per gram, so in that sense, it's really good. But there's a big but. It's got this super short half-life, only 138 days.
138 days. So basically, by the time you got a spacecraft to Mars, it would already be half as powerful as when it launched.
Yeah, pretty much. Not ideal. Not at all. Especially if you're thinking about missions that last for years. So that was a no-go. Then they looked at Curium-244. That one's got a decent half-life, about 18 years. And it's got way more power density than plutonium-238, like 5 times as much.
Sounds promising. What's the problem with that one?
Well, the problem is it emits a lot more radiation, specifically gamma rays and neutrons.
Which are not good. Not for the spacecraft itself, and definitely not for any humans that might be involved.
Right. And shielding against that kind of radiation is really difficult. It adds a lot of weight, makes the whole thing way more complex. And then there's the issue of producing it. Making Curium-244 in the quantities and the purity you need, it's really expensive, really complex. It's just not practical right now.
Okay, so we've ruled out polonium because it fizzles out too quickly, and curium because it's too hot to handle. Any other contenders?
One more. Galdium-148. This one's got a really long half-life, emits only alpha particles, which are pretty easy to shield against, so that's good. But the big problem is how you make it. You need these incredibly powerful, incredibly expensive particle accelerators to even produce it. And we just don't have the facilities right now to make it on the scale that we need for space missions.
Okay, so it sounds like we've looked at all these alternatives, but we keep coming back to plutonium-238.
Yeah.
It's got that sweet spot of, long enough half-life, manageable radiation, and a pretty good track record of stability. I mean, some of those generators that were recovered from those failed launches decades ago, they were still in pretty good shape, right?
Yeah, surprisingly good shape.
So it really is the Goldilocks of space power, isn't it? Like, it's just, right.
I think that's a good way to put it, yeah. It meets all the requirements.
So, okay, we understand why it's so good, but how does it actually work? I mean, we've got this radioactive material giving off heat.
Mm-hmm.
How do you actually turn that into the electricity that runs a spacecraft? It's not like they've got power outlets on Mars.
Right. Well, the current technology uses something called the thermoelectric effect, sometimes called the Seebeck effect. It's a bit complicated, but basically, if you have a temperature difference across certain materials, like semiconductors, you can create an electric current.
Okay, so it's like using heat to directly create electricity.
Exactly. In these, what they call RTGs, radioisotope thermoelectric generators, they use 2 different types of semiconductors, a P-type and an N-type. And when one side of these materials is heated up by the plutonium-238 and the other side is kept cool because it's radiating heat out into space, you get this flow of electric charge. And that creates the voltage, the current that can power the spacecraft.
So the constant heat creates a constant flow of electricity. It's elegant, really, when you think about it. But from what I've read, this whole process isn't actually very efficient, is it?
You're right. Unfortunately, it's not. Right now, these RTGs, they're only about 6 or 7% efficient, so most of that heat energy is basically wasted. But there was this other project, the Advanced Stirling Radioisotope Generator, ASRG.
ASRG.
Yeah, that one used a completely different type of engine called a Stirling engine to convert the heat into electricity. And it had the potential to be way more efficient, maybe up to 30%.
30%? That would be amazing. So what happened to it?
Well, they worked on it for about 10 years. It showed some real promise, but ultimately the project was canceled back in 2013. Too many technical challenges, cost overruns. You know how these things go.
Yeah, unfortunately.
So for now, we're stuck with these less efficient RTGs, which just makes it even more important that we figure out how to make more plutonium-238.
Absolutely. So let's dive into that process. How do we actually make this stuff? It's not like we can just dig it up, right?
Right. It's a multi-step process, and it all starts with another element called neptunium-237. Turns out, we actually have quite a bit of this stuff left over from the Cold War. They were making plutonium-239 at the Savannah River site, and neptunium-237 was a byproduct. And luckily for us, it's got a super long half-life, millions of years, so the stuff they made back then is still good today.
So we're using a Cold War leftover to power our future in space. That's interesting.
It is, isn't it? So anyway, they take this neptunium-237, which is usually stored as a liquid solution, and they ship it to Oak Ridge National Laboratory in Tennessee.
Oak Ridge, famous for its nuclear history.
Exactly. And at Oak Ridge, they do a bunch of chemical processing, purifying it, turning it into a powder, pressing it into these little pellets, and then encasing those pellets in aluminum. And this is all to prepare it for the next step, which is irradiation.
Irradiation, so they basically bombard it with neutrons in a nuclear reactor.
Exactly. And they use some serious reactors for this, like the high-flux isotope reactor at Oak Ridge and the advanced test reactor in Idaho. Inside the reactor, the neptunium-237 absorbs some of those neutrons, and that turns it into neptunium-238. But that stuff is unstable, so it quickly decays into plutonium-238. It's basically a chain reaction, but a controlled one, happening inside these incredibly powerful reactors.
So we're using nuclear reactors to create the fuel that will power spacecraft to other worlds. There's some poetry in that, I guess.
Definitely. It's a fascinating process when you think about it, but it's not easy. It's not like you can just stick the neptunium in the reactor and out pops perfect plutonium-238. It's a really delicate balancing act.
How so?
Well, first of all, you have to control how long you're irradiating the neptunium. Too short, and you don't get enough plutonium-238. Too long, and you start creating other unwanted isotopes. And you also have to worry about something called fission.
Fission, that's when the atom basically splits apart, right?
Right. And that can happen with both neptunium and plutonium when they get hit with neutrons. So you're constantly losing some of your product to fission, and you're creating these other isotopes that you don't want. It's a real challenge.
So once the irradiation is done, you've got this mix of stuff, right?
Yeah.
How do they get the pure plutonium-238 out of that?
Well, it's a whole other set of complex chemical processes. They basically dissolve the irradiated material in acid and then use all sorts of techniques to separate the plutonium-238 from everything else. And they have to get it really pure, like at least 85% pure, because any impurities can affect how well it works in the RTG. And once they've got it pure, they turn it into this ceramic form, which is super stable, and that's what they ship off to Los Alamos National Laboratory in New Mexico to be made into the final fuel pellets.
So it goes from Indiana to Tennessee to Idaho and finally to New Mexico. That's quite a journey.
Uh-huh.
And it sounds incredibly complex. Like every step of the way, there are these potential problems, right?
Mm-hmm. Oh, yeah, totally. I mean, it's amazing they can do it at all, really. Like you said, it's not like flipping a switch. It's this whole chain of incredibly complex, incredibly delicate processes all happening in these very specialized facilities.
And we're not exactly churning it out, are we?
No, not at all. Oak Ridge is hoping to get up to a production rate of about 1.5 kilograms per year.
1.5 kilograms, so just over 3 pounds.
Right. And to give you an idea, the Dragonfly mission, just that one mission, is going to need almost 5 kilograms of plutonium-238.
So 3 years of production at best for one mission.
Pretty much, yeah. And that's just Dragonfly. There are all sorts of other missions being planned that could use plutonium-238. It's a major bottleneck, and it's only going to get worse as we get more ambitious with our space exploration plans.
Okay, so what's the solution here? How do we get more of this stuff?
Well, the obvious answer is we need to scale up production, right? Build more facilities, streamline the process, figure out ways to increase the yield. But that's easier said than done. It's a huge investment, both in terms of money and expertise.
Right. And it's not just a U.S. problem either, is it? Other countries are facing this shortage too.
Yeah, absolutely. And the good news is other countries are starting to take notice and get involved. The European Space Agency, or ESA, they're looking into setting up their own production capabilities. France, too.
So maybe some international cooperation could help ease the burden a bit.
It could. And having multiple sources of plutonium-238 would definitely make things more resilient, less vulnerable to disruptions. So that's a positive step.
Okay. So we've talked about plutonium-238 powering these missions to the outer solar system, but what about closer to home? Like, could we use it for missions to the moon?
Yes, absolutely. And in fact, there's growing interest in using it for lunar missions. You see, even though the moon is much closer to the sun than, say, Saturn or Jupiter, there are some places on the moon that are permanently shadowed. Like these craters at the poles, they never get any sunlight.
And those areas are really interesting, right? I remember reading something about them possibly having water ice.
Right, exactly. They could hold these huge reserves of water ice, which would be incredibly valuable for a future lunar base or even for producing rocket fuel. But the problem is, you need a reliable power source to operate in those permanently shadowed regions. Solar panels won't work.
So plutonium-238 is the answer there, too.
It could be, yeah. It could power rovers, landers, even habitats in those areas. So it's not just about the outer solar system anymore. It's about enabling us to explore and potentially even settle other worlds, starting with the moon.
Okay, so plutonium-238. It's a Cold War relic, it's a limited resource, it's a complex and challenging thing to produce. But it's also the key to unlocking so much of what we want to do in space. I mean, it really is, like we said earlier, a kind of miracle fuel.
Yeah, it is. And the big question now is, are we willing to make the investment to get enough of it? Because if we want to be a truly spacefaring civilization, it seems like we're going to need a lot more of this stuff. So it's not just a technical challenge, it's a policy challenge, it's a societal challenge. It's about deciding what our priorities are and what we're willing to invest in to achieve them.
Deep stuff.
Yeah. And I think that's a perfect place to leave it for our listeners to think about.
Totally. Thanks for diving into this with me. It's been enlightening, to say the least.
My pleasure.
And to all our listeners out there, keep looking up.